I hope you all can hear me and see my screen feed clearly. Good morning, Manu. Good morning, Anamitra. Let's start with the class, and after the class, we will gather on Google Meet to discuss anything which is relevant. A very good morning to all of you. In today's class, we are going to talk about noise removal with spatial filters. We are going to look at some type of filters, mean filters. We will look at harmonic filters. We will look at order statistics filters. Now, just to put things in perspective, let me talk what we are doing. So we have already learned a lot of imaging so far, and in the last few lectures we are talking about image restoration. Now in case of image restoration, we are looking at noise removal to be particular right now. The noise removal is a very important idea. Images may contain lot of noise, variety of noise, and yes, we have seen those noises, types of those noises and those noise models in the previous class. Now in this class, of course, our aim is to reduce the noise mostly. I mean, unless otherwise you want to enhance the noise deliberately, we will reduce the noise and talk about some of those filters. Now, as the name suggests, the mean filter we have already spoken of in the earlier class. So this class, in this lecture, we are not talking about the particulars of a particular filter, but a grand overview of some of the filters. So I go ahead. Now if I take an image with noise only, then the image equation looks like this. Remember, we are talking about additive noise all the time. We are not talking about the noise if it is multiplicative. So if f of xy is my original image and eta xy is my noise, then noise can be added to the original image and g of xy is my final image. Now, in case of frequency domain, the same equation can be written in this way. Now, what typically happens in our day-to-day life is that you get g of xy. So noisy image is known to us, but you don't know noise. Noise is generally unknown. So noise is not known to us. And your target is to extract f of xy. So look at it. I mean, this is given and this you have to determine, but you don't know anything about this thing. So remember, we have developed some of the strategies in the previous class. One of the strategies is to use noise modeling. Find out a small sample or the patch of gfxy where you assume the intensity should be uniform and it is not uniform because of the noise. So take that small patch, you apply histogram analysis to it and see the shape of the histogram, and from that you try to gaze out what kind of noise is there and then look forward to the best strategies to eliminate those noise. So that is the strategy that we are going to employ. Now when we are starting with this lecture, we always assume that we have already obtained the noise parameters by this sampling technique. Now, what are the different kind of filters that we can use to suppress this noise? So let's see. So one is the arithmetic mean filter. We are already familiar with arithmetic mean filter. Remember, we had applied those box kernels 1 3 by 3, and the size could have varied from uh, 3 by 3 to 5 by 5 to 10 by 10 to 50 by 50, depending upon the requirement. In a mathematical process, I can write it in this manner. So what how is this equation, or what does the terms in this equation mean? So let me see. Sxy is a small neighborhood, it's a small region in the image where I'm applying this spatial filter. G of RC is a particular pixel value in this small neighborhood. Now it is this neighborhood which determines the size of the pixel. So neighborhood could be 3 by 3, it could be 5 by 5, it could be 7 by 7, 11 by 11. Remember, we have discussed this, that mostly we keep the sizes in odd multiples. So M and N are the rows and columns in your this small neighborhood. If both are equal, as in 3 by 3, 5 by 5, 7 by 7, then this is just a product. So if it's a 3 by 3 matrix, this is 1 by 9. If it is 6 by 6, 5 by 5, then it is 25. Then G of RC is the value of individual pixel in this neighborhood. So RC are the dummy variables which can start from 0, 0 to m minus 1, n minus 1 in this neighborhood. So all it says is that you take a small neighborhood of S of xy, take all the pixels in that neighborhood, you add all those pixels together, and once you have taken all the pixels together, then divide it by the total number of pixels. This is m by m into n is total number of pixels divided by total number of pixels. Whatever value you get, you assign that value to the center pixel, to the center of this neighborhood. So where the pixel which is central, pixel from the image which is central to this neighborhood. So that is how you do your arithmetic. Remember, this process is again the convolution process. So this smoothing smooths out the local variations in the image, and noise is reduced as a result of blurring. Remember that this also constitute what is called as a low pass filter. High frequency components are blurred out or suppressed. I have an example over here. This is an image which is corrupted by Gaussian noise. So you have a Gaussian noise of some standard deviation applied to it. Now I'm applying a filter here, and mostly it is a 5 cross 5 filter, blurring filter. You can see that as you go from here to here, there is a considerable amount of blurring to the entire image, but also remember that these small dots have almost gone. There is a suppression of the noise. Now on the very same lines, once you have understood one, understanding others is easy. This is called geometric mean filter. In a geometric mean filter, instead of adding all the terms, you multiply all the terms together. So take individual pixels of the neighborhood and you multiply all of them together. This symbol represents, just like sigma is summation over a series, this is a multiplication over a series. You have used these kind of symbols in your mathematical physics course, molecular physics course, modern physics courses earlier. So that is what. So yeah, so here this gives you the product, and then you take 1 over m by nth root of that product. Why do you want to take this 1 over m by nth root of the product? Think about it. So yeah, so that gives you the geometric mean filter. The geometric mean filter achieves smoothing comparable to arithmetic mean filter, but tends to lose less image detail in the process. You had just seen that in arithmetic mean filter, the details loss were quite considerable. Also think about many other parameters, and one of the important thing to think is what happens if a particular GRC is 0, then the entire product will become 0. So do think what could happen to the image at that point. Then a new type of filter which is called harmonic filter. It takes the reciprocal of each of the pixel values in the neighborhood 3 by 3, 5 by 5, whatever neighborhood you define. It takes the reciprocal of all the individual pixel values, then sum it all together, and then that summation divides m into n, total number of pixels. So whatever value you get, that is assigned to the central pixel. So when you take a reciprocal, you actually uh, flip the intensities. But remember, this is a reciprocal of reciprocal, because this whole thing is in the denominator. So eventually you regain your intensity back. So it works for salt noise but does not work for pepper noise. So if you have a salt noise in your image, then this is a very good feature. And there's a contra harmonic mean filter, which is a little bit of modification of the previous one, just that here the q is a variable. So you take all the values in the neighborhood, you apply some power to them, q plus 1 here and q here. So remember, 1 plus 1 power on an average would be left out after this computation, and that value is assigned to f of x plus y, f of x plus y. So q is called the order of the filters. You can have order 1, order 2, order 3, etc. For positive values of the q, the filter eliminates pepper noise. For negative values of the q, it eliminates salt noise. So I'm not giving you any example. Wherever I'm not giving you example, please refer to the reference books. It gives you many examples for each of these filters. And then the contra harmonic filter. Yes, here is an example for contra harmonic filter. So you can see that you have pepper noise, and you apply the contra harmonic filter and the pepper noise is almost vanished. Then comes the order statistics filter. So as the name suggests, it's a statistical order. So you select your neighborhood first. That is the first step. Geometric mean. Manu, you are asking, isn't that the definition of geometric mean? About which slide did you ask? Please mention. I have come a little ahead. So order statistics filter. So you take all the neighborhood, take all the pixels in the neighborhood, and you arrange them in a particular statistical order. So either you arrange them in an increasing order, or you arrange them in a decreasing order, or in whichever way you want to have a definition. So you can arrange them in an increasing order and create a median filter. Okay, Manu, thank you. Yeah, we'll go back to that in the post-lecture discussion. So, so how does a median filter define? Very simple. You first select your neighborhood. So you have already selected your neighborhood. Then you arrange all the pixels in that neighborhood in a statistical manner, increasing, decreasing, whichever is suitable. Now for median, you know that if you arrange them in the increasing order, then the central value pixel is your median. So we can select that pixel and assign that to the center of the resulting image. So this can be done again. The method remains exactly the same that we have learnt in previous chapter, just that their noise reduction was not in focus. Here the noise reduction is in focus. So median filters are very interesting and very important filters. They produce much less blurring and do a very good job over smoothing. They also remove both salt and pepper noise because, by definition, salt and pepper noise are at the extremes, either at bright, very high pixel value, or dark, very less pixel value. So, this median filter offers a middle pixel value, and therefore it eliminates both salt and pepper noise at one shot. So it's very effective in presence of both bipolar noise. The salt and pepper noise is also referred as bipolar noise because the intensity values are at two poles, very bright and very dark. Here's an example for median filter. So I have my corrupted noise, but remember here's a Gaussian corrupted noise. And this is the result of 3 by 3 mean filter, the mean filter that we have learnt earlier. And this is the result of 3 by 3 median filter. So you can see that the order of the filter is of the same size. The impact of noise removal is also largely the same, but you can see that this has more sharpened structures while this has got more blurred. Look at an overall view of the image, not the micro view. You will find that these mountains ranges are very sharply defined. Here they are not that sharply defined. So you can see, you can make out that difference. Another order statistics filter is your maximum filter and minimum filter. So a max filter, so remember, once you have ordered your neighborhood in a statistical manner, then you can derive just as you derive the median filter, you can also derive max and min filter. The max filter is the maximum value of the pixel in that neighborhood, while the min filter is the minimum value of G or the pixel in that neighborhood. So both of these can be utilized from the same ordering structure. Their usefulness could be different. For example, the max filter, as the name suggests, it picks out the brightest pixel in that given neighborhood. So what it does is it enhances the bright regions or the bright points in the neighborhood, while it suppresses the dark points. So it erodes the dark regions. So that is the function of the maximum filter. The function of the minimum filter is actually reverse. It selects the darkest point or the minimum pixel value in the given neighborhood. So it enhances the darkest region, also suppressing the bright region. So it does a reverse operation. So depending on what kind of image you have, you can put these filters to work. Oh, this is repeated. So yeah, here is my original image. I'm not looking at the corrupted with noise. I'm just looking at the original image in order to enhance this point. Now here I'm applying a minimum filter. You can see that these regions will not show much difference, but look at the regions like this. This has been suppressed. The brighter point has been suppressed considerably here, and the darker points are now dominating. For example, here you can make out a very faint road going up, which has vanished here. And this is applying the maximum filter. Once you apply the maximum filter of the same size, you can see that all these brighter regions has become more brighter. This road has become more dominant, while the darker regions have been eroded. So the darker regions will be suppressed. So yeah, another order statistics filter is midpoint filter. Midpoint filters are again very important, just they are like median filter. So you arrange them, take the middle value, but this is not the middle value from the order, but it is the actual mid value. So you take the maximum, you find the maximum in a given neighborhood, you find the minimum in the given neighborhood, and you take an average of the two. And that will give you the midpoint. Remember, it differs from median. Median is you arrange them in order, take the central pixel. That is median. Here it is slightly different. So it combines order statistics. That means you first put everything in order, increasing or decreasing, and then you put an averaging. So you are taking an averaging filter. So this works good for randomly distributed noise, Gaussian noise, or uniform noise. So yeah, we that's all for today's class. These filters we have today discussed are called filters in the spatial domain. Next class I'm going to repeat or again talk about filters in frequency domain, how to identify periodic noise and filters to eliminate them. But till then, thank you. We will meet now in Google Meet.